So we've been talking about solute transport, and we end up with the solution for an instantaneous injection of material in an infinitely long column. So I've got a column of sand here, and I'm going to put in an injection at time equals 0. And what's going to happen is this region of material, let's suppose that the water's moving this way, it'll spread out. Okay? But it's going to still be more concentrated in the middle, less concentrated at either end of the plume. Okay. Now, this solute moves at a velocity u, okay? And so when we look at the solution, we see that, yes, the peak concentration, since this is negative, the peak concentration happens when this term is 0. So this is, since this is a positive number, this is a positive number, but there's a negative sign there. As this gets bigger, everything else gets smaller. And so the peak concentration happens when x equals ut. So that's a translating wave of contaminant moving down through the column. This form, the x minus ut squared, is a Gaussian curve. Or a bell curve. Okay, so we know that that is what's called the normal distribution, and so it's going to have a nice little form like that. This is going to be at the center of mass. And then it spreads out either way symmetrically in space. So we're drawing x in this way, okay? So x only shows up here, and so as I go smaller and larger, since this is squared, it's symmetrical. It gets squared, so it has exactly the same value, and it has a classic Gaussian curve. Now, the thing that I want you to think about, though, is very rarely do we get to actually watch a plume moving through soil. What we typically will do is we'll put in a sampling point. There's our sampling point. So what we're actually going to do is watch in time the plume come by. Now let's look at time. Time shows up here as we saw before like x, so in a sense you think it'd be symmetrical, but time also shows up here and here. So as time goes on, this number gets bigger, so that reduces the size of this, and this number gets bigger, which reduces the size here. And we also will talk about degradation in a moment. This is degradation. We're not going to deal with degradation quite yet. So what happens in time is that the curve will start off abruptly high, and then it'll go out and tail off. So when we do time as our axis, what we see is that it's steeper as we first start seeing the plume, but then as this plume keeps on spreading, as it's going by, it has a longer tail. And so what I want you to really take from this is the fact that watching in space and watching in time give fundamentally different shapes. And this, which we call the breakthrough curve, the breakthrough curve is watching in time. That's by far the most common thing to have, and it will always have an extended tail, regardless of if there are other processes or not that might spread the solute further. Even in an idealized case, it will have this extended tail in time, but not in space.